In this video, folks, we're going to be looking at impulse and momentum, two interesting quantities that lead us to a new conservation law. Um, and we're going to look at a few examples of how this works. I'm going to do a couple of demos for you. So the first thing is momentum. We have to define it, of course. And momentum can often be thought of as mass in motion. You've probably actually heard momentum used. Well, we've got a lot of momentum going. Let's just keep moving on. Sports teams like to say these kinds of things, or at least commentators do. They got a lot of momentum going into the election season. They got a lot of momentum going into the playoffs. And it comes, I think they're related to the really physical idea of momentum. But we know that any object with a mass has an inertia or a resistance to a change in motion. And any mass that is moving has momentum. So to determine this momentum of the object, you simply multiply its mass times its velocity. And momentum is this vector quantity that is mass times velocity. The units of it are a kilogram times a meter per second. It doesn't get its own special unit, which is interesting. It is a vector, and that is because it's a scalar mass times a vector velocity. So momentum and velocity have the same direction. We do have to be careful about that. All of the energy stuff, we were kind of getting rid of direction most of the time, but it's back. Couple of important things you might think of this to yourself. Turn to someone near you. Obviously, I don't have a neighbor today, but what is something with a very large amount of momentum? And this can be interesting if you think of a massive, freight train, a mile long. If it's at rest, it has no momentum. But if it's moving even a little bit, that huge mass and small velocity leads to a lot of momentum. Meanwhile, a very small object but flying super fast, like one of those tiny little pebbles of space dust whizzing at 1,000 miles an hour around the Earth in orbit, are incredibly dangerous to a spacecraft because they're flying so fast that even with their small mass, they have a lot of momentum. So different ways to get large amounts of momentum. The other idea we have to talk about is impulse. And the relationship between impulse and momentum is really what Newton was talking about when he was talking about his first, second, and third laws. He didn't talk about them in terms of forces and acceleration the way we usually think of them. He actually spoke about them and wrote about them in terms of what he called impulses and momentum. So whenever two objects interact, we know from the third law that they apply a force on each other. And if they apply a force for some amount of time, that is what we call an impulse. So an impulse would be anything, going and touching something for a small amount of time, bumping into something, any force applied for any amount of time. Right. So here's an example of an impulse. This is kind of a dramatic one. This is a time-lapse photograph of a racquetball. Picture 1 is just as it's about to hit, and picture 12 is just as it leaves the surface. It almost looks like a red blood vessel right there at number 5, which is kind of fun. But that's when it's sort of like maximum compressed, and then it starts to push back out. And we can think about this individually, right? We could say, oh, before contact, the force on the ball is 0. Then the force grows, it's greater than 0. Then the force reaches its max at some point from the wall and the ball. And then the deformation lessens and goes down. But you could also, if you wanted to, talk about not the force of the wall on the ball, but the force of the ball on the wall, right? It's 0 at the beginning, but then you could draw it in that equal and opposite magnitude. It gets really big, and then a smaller force at the end, right? This is what happens with the third law. And so this could be thought of as a third law situation, but what we're going to think about it as is an impulse situation. Taking a step back, we'll go back to that example and the fact that it's not as simple as we might like. But impulses change velocity. That's what Newton said. And that's essentially analogous to a net force causes an acceleration. A change in velocity is an acceleration. If you imagine that ball was headed to the right with the speed of positive v, and now it's headed to the left at the speed of v in the negative direction, the change in velocity is negative 2v. There is an impulse because there is a change in momentum. Momentum was changed by a factor of 2. When an object gets an impulse, that changes its momentum. This is what we call the impulse momentum theorem, and it's analogous to the work kinetic energy theorem. But how do we define impulse? Well, we generally say that impulse is a force multiplied by a time. It is, again, a vector, because force is a vector and time there. Notice I've highlighted average, because usually in these kinds of collisions, the force is not actually a constant. So we have to be a little bit more careful. Just like work being force times distance, if the force wasn't constant, we had to be a little bit more careful. So again, this is a vector. And so I want to show you a couple of examples of how an impulse causes a change in momentum. So I'm going to switch over here. This is the example that I'm going to start with. It's a force probe or a cart that measures force attached to a barrier. I've got an example where it's attached with a rubber band. This graph here was actually, I think, with a little string that I did a long time ago. I don't even have that video anymore, but do I have that vest? Maybe. Anyway, but I recorded this one just the other day. And so we've got this little yellow cart on the ramp. And as it is allowed to go down the ramp, and be caught by this rubber band, we'll measure a force on it. There we go. And you notice there are these forces as it bounces. So let's think a little bit about what's happening here. We see that the velocity graph, it increases at first, right? That's just it speeding down the ramp after I let go of it. Then it reaches some maximum value here, and then it, of course, decreases, changes direction, and speeds up in the negative direction. So that's a big change right there. And that corresponds to this place where there was a big force over some amount of time. And I can actually find the integral, or the area under that curve, of the force multiplied by time in Newton seconds, negative 0.345 Newton seconds in this case. And down here, I could look at what's going on, and I could say, well, we have a maximum value of 0.486 meters per second and a minimum value of negative 0.365. We could think about the change in velocity here. And if we knew the mass of the cart, we could see that it equals that change in velocity times the mass, or the change in momentum equals that integral of, force times time in Newton seconds, or kilograms meters per second. You'll notice that over here, once it bounces the second time, it's slowed down a little bit. And so we get a smaller impulse. But we also have, of course, a corresponding smaller change in velocity. We could do that over here again smaller. We've got a smaller impulse, and so on and so forth, right? You keep getting smaller and smaller as there is some energy loss here. So just because there's a nice impulse momentum relationship doesn't mean we didn't lose energy, which is kind of an important thing. There are a couple other things we can look at, different types of collisions, and which is also interesting. I'm going to get rid of this video and all of this for a moment, and I'm going to just go on back to some graphs. I'm going to switch it up, and instead of being on that incline going down, I took one where I pushed a cart up against a wall with a rubber stopper, right? Gave it a push, it banged against the wall. That's a very sharp impulse, right? That's something where you smash into the wall and you stop quite abruptly. And we see a pretty fast change in velocity there. So that's that first one. But then you can do other things, right? I also took some where I attached a spring to the front of the car. I was going about the same speed as the other one. You can see a little bit slower to begin with. Here's our change. But the change in momentum, the integral there, was different, right? My areas are both negative 0.5 something, but we have a much smaller area, or a more spread out area, wider but shorter. We can keep changing this. I can, instead of that spring, I could do a piece of string to stop it, which is the most dramatic one. That one's, a very sharp one. It happens very quick. But so all these different things, the sharpness of the peak determines how fast the rubber band or the object changes its velocity. And we get an impulse, an area under the curve of a force time graph equals a change in momentum. So let's switch back to this view again and think a little bit about what we can calculate. This is a little calculation example. How if you knew the mass of the cart, you could see that the area under the curve and the change in momentum were indeed the same. But when we say impulse, it relates to this idea of Newton's second law, right? Newton's second law says acceleration is change in velocity over time, and that change in velocity over time replaces the acceleration in our Newton's second law equation. And we can rearrange that and get force multiplied by time as mass times change in velocity. And that highlighted thing really is the impulse momentum theorem. And so what does this tell us? Well, it tells us that if we have a constant or average force, right, we can predict how much the impulse will change its momentum if we can just figure out how long that takes. And impulse gets this symbol J. You don't actually need to know this bottom version of this equation where it's an integral of f dt, but that implies that we could figure this out even if the force is not constant, which it wasn't in any of those previous examples. So let's look at an area under the curve, right? Here's sort of the impulse highlighted in red, a force from time interval initial to final. And so if you think about anything you do, if you kick a ball, right? Newton's third law would tell us that the force that the ball applies to the foot and the foot applies to the ball would be equal and opposite. Well, if that's true, then impulse, which is just force minus multiplied by time, must also be equal and opposite. It's because you can't be in contact foot with ball longer than ball with foot. So they both are there, related quantities. So an impulse isn't change in a momentum. It could do one of three things. It could speed the object up, slow the object down, or change the object's direction, just like acceleration could. We have to watch our signs. Remember, these are indeed vectors. So a couple of quick examples to wrap us up today. So the impulse momentum theorem tells us that the area under this curve, the force times time, is going to be equal to the change in momentum. So we're just picking an arbitrary object, a blob, as I've said here. And the force on the 10 kilogram blob starts at 0, increases to 60, and then decreases back to 0. I've picked one that's a nice triangle with kind of reasonable shape here to make it easy. If we know the mass is 10 kilograms, the initial velocity is 0, we also know the initial momentum is 0. We can then calculate the impulse as the area under that curve or that triangle to give us 120 Newton seconds. And then we can solve for V final, 120 Newton seconds divided by that 10 kilograms. Gives us 12 meters per second, remembering that a Newton is a kilogram times a meter per second squared. If the curve is not geometric, there's lots of ways to do this, divide it up into little squares, figure out what they are approximately, right? And add them all up. You can still get a value there. That's, the gist of solving a problem like this. Another example. A baseball has a mass of 0.14 kilograms and an initial speed of 30 meters per second. It rebounds from the bat with a speed of 40 meters per second. Now, this one's interesting because there is more energy in the ball after than before. That's because presumably someone was swinging the bat, right? That's the whole goal. You want to get that ball to go somewhere. And so we know this isn't an energy conservation problem. This is an impulse relationship. But what it can tell us is not how much force we had at any given moment, but it could tell us what is the average force while the ball is hitting the bat, knowing that the maximum force would be much bigger. And of course, the minimum force is 0. But it does give us some information about what it would take to accelerate this ball. Impulse is change in momentum. Impulse is force delta t. And the delta t, we're told, is 2 milliseconds or 0.002 seconds. All right, to wrap all this up, what do we know? Well, we can say a couple of things. Our big ideas. We've got impulse is a change in momentum. Momentum is mass in motion. Those are the two big ideas, right? If you apply an impulse of force multiplied by time for some amount of time, you get a change in momentum. This is basically Newton's laws revisited in a different way. There's lots of interesting consequences to looking at it this way, which we will get to as we go through this unit.